Hello everyone, this is Group Three's midterm video presentation for our project, the IR finger vein imaging system. In our group, we have two computer science engineers, we have one electrical engineer, and we have two photonic science engineering students. So the imaging portion of the project was done by Jessica, and here we can see the layout for testing the imaging portion. This layout will be modified before the final project, and it will look something more like the first CDR that was turned in. But for testing purposes, we decided not to have all our stuff boxed up, so we decided to test the layout this way. Right now on your screen, we can see our screen that we were testing with. And as we keep moving on in the video, in this portion we can see our lighting. So instead of using a laser diode, we decided to move forth with an LED. This was because although the laser diode did create a speckle pattern that was usable and the image was usable, to get the results that we wanted out of a speckle pattern, we would have had to merge images. And for the sake of getting our results back in time in the system, we decided to move forth with an LED. So here we have our LED, our singular LED. Here we still have our beam expander, but in this case, because it's not a diode, a laser diode anymore, we're not expanding, but we're compressing and culminating our beam now. And then we have our diffuser, which is still needed to not have a really peak intensity in the picture. Now down here are some other LEDs that we were using while testing, but we found out that through testing we only really need our one LED. Now this is the secondary camera that's used by the computer science engineers to be able to get commands out of hand movements, because the main camera for authentication is an IR camera, and it is seen over here. So that is our IR camera, and it is facing the screen for authenticating purposes. We have to have it this far in order to get the correct field of view in the picture to be able to analyze our vein patterns. And this is an updated picture of what the picture looks like actually in the IR camera for authentication purposes. Since the lighting was switched, we decided to show what the IR camera is picking up now.
So here we show a proof of concept working. I put my finger up to some barriers to have proper placement for the camera. And as soon as I put my thumb out, it'll start capturing images through the infrared sensor. And in this specific scenario, I am the only one that is eligible for signing in or authorization or whatever the scenario might be, because I am the only one that has images saved in the database for comparison. So here we have, as a result, me being validated there. It says you shall pass, which means it works. And then in this next example, or this run rather, we have a manual attempting to get in. Since he is not in the database, he should not be eligible for passing. And it'll take several screenshots and then start comparing them to the saved database. And then eventually here we will see that it will return print statement saying you shall not pass. Also, it's worth noting that we don't need to keep our hand there. As soon as this part starts running, we can just relax.
Good day, my name is Emmanuel Cortez, and I'm going to be going over part of the code functionality for our project. We make use of different libraries and modules that we created. We predefine locations like file directories, our cameras parameters, and we initialize modules that allow us to determine the hand's position or the hand gestures or how the hand is placed. Then we go through an infinite loop where we intake the image captured from a webcam and we process that image to determine the fingers position and if they're up or down. Based on, for example, based on the result of the index finger being active as an up, we then start a timer where we wait for the predefined time to start the capturing of the images using our sensor, our camera sensor Vimba. Based on the image capture, we do some cropping, and we send all the images down to the machine learning, the model, and we get a result. And based on that result, we can determine if the person passes as in is it the correct user or if it's not. Taking a look at our hand detection module, which is in essence is all the parameters for MediaPipe in order to activate it and be able to use the hand in determining if fingers are up, if hands are down, if fingers are up, if the landmarks in the hand, and that's what basically this module does. We have our gesture detection module, which basically controls a timer and allows us to determine if how long the index finger has been up, and if it has been up for the predefined time for capturing image, then it returns a true, which allows us to later from commands.py allows us to capture the image using our Vimba sensor. With our Vimba sensor, which is this module, we initialize a couple of threads. We initialize the call for whenever the threads are called to shut down. Then we also predefine the setup for the sensor as an exposure and the balance and white out. We also set up the color format, which for this sensor is a mono 8. And whenever we store the images, we first convert the image to from a Bayer's gray to an RGB format. We crop the image and we store it locally. And all that is managed through the command.py. Thank you for your time.
For the one-shot module, we utilize the TensorFlow and Keras library for building the machine learning model and then utilize OpenCV and NumPy for pre-processing the images that are to be sent to the ML model for prediction. We first start with the building of the Siamese model using TensorFlow's API. We define first the two input images that the neural network will take in for prediction. Secondly, we create the neural network, convolutional neural network itself. Third, we create the encodings for the feature vectors for the two images. Next, we create a custom layer that computes the differences between the encodings. And then lastly, we add an output layer with a sigmoid unit that will generate our similarity score. The image process function prepares raw images for the neural network. It first resizes the images to prepare for the neural network, and then in order, it performs canny edge detection, dilation, and then adaptive thresholding on the images. And here is an example of some of the images being processed. The first similarity score was given after a comparison between the first image, which is from Jordan, and the second image, which is from Emmanuel. And then the second score is between the first and the third images, which both belong to Jordan, resulting in a higher score.
Now, let's talk about the projector system. The first component of our system is a heatsink, where the 450 lumen chip-on-board LED is mounted. All the light produced by the LED is redirected by the reflector and the Fresnel lens. This will produce a collimated beam of light that will pass through a polarizer. A 3.9 inches LCD with a resolution of 800 by 480 will generate a color image. To reduce the light loss in the system, a second Fresnel lens is used to gather the light. To fit the length of our system inside the device, we use two mirrors to steer the optical path length. A Cook triplet optical system is mounted with a 147mm biconvex lens, then a negative 50mm biconcave lens, and finally a 60mm biconvex lens. At the end of the system, we use another mirror, but this time the optical path direction points downwards. Once everything is set up, the projector will invite the user to place the hand in the right position. Drawing arrows in the user hand will guide the user to properly place its fingers in the right location. When the hand is detected, the verification process will start, and the vein pattern analysis will take place. If the results are positive, a success message will be displayed in the user hand. Otherwise, if the initial reading got a low score, a message will be displayed with a negative output. When a user is not registered, an animation will show the hand gesture needed to input the information in the database.
This is the PCB for our project. What this is intended to do is supply 12 volts to our projector and 5 volts to our Jetson Nano MCU. What we have right now is the charging cable plugged in and the switch is not turned on, so all it should do right now is charge the batteries. We're going to test to see 5 volts coming in, which we have. And then out of the first circuit, we should have 4.2 volts, which charged the batteries. We have 4.1, which is close. Following this run to the batteries, we end up with 3.9, which is due to a voltage drop from this long run. Going into turning it on, we're just going to put a jumper on it, and we have the LED lights which shows the charge of the battery. Right now, since the cable's plugged in, we're only showing the charge of what's being supplied, which is 3.9, which should also be 3.9 at the battery. Yep. And then from here, we should get 5 volts at the USB ports and 12 volts at the DC jack. There's 12 volts at the DC jack. And then right now we don't have 5 volts at the USB ports, but we do have 3.5. I'm still looking into that.